And hello everybody, welcome back. Welcome back YouTubers, fellow OpenFoamers. Okay, today we'll continue our discussion from last time. We were talking about thermophysical properties and showed you guys what it means. Excuse me. Now we're going to look at boundary radiation properties. Okay, so let's see whether we can find this online. Okay, so OpenFoam. Okay, so there are some guides. It's an API guide. Okay. So this will tell you how to do how do you say? Give the input files and everything. So this is under radiation. This looks like more C++ looking things. Okay, so the C++ files is here. Man, yep. This one may not. Okay, as of now, you look at all these syntax and everything. It may seem pretty intimidating. So, okay. You'll skip this for like a more advanced kind of time. Yep, so okay. This is a very C++ thing. So okay, let me try something else. Alright, just ignore the C++ lingo. So basically we have emissivity, which accesses a boundary emissivity. So this is a strictly boundary condition kind of thing. Again, absorptivity. This one will access the boundary absorptivity. Okay. The other stuff, okay, the documentation is a little bit complicated because then you're expected to know more C++ and it can be pretty intimidating. So I'm not going to do that now. Okay. So just know that this is the whatever boundary that you have at the sites, this will be the absorptivity and emissivity. Okay, let's take a look at radiation properties. So this is for the body. Okay, so we have something called radiation on, radiation model P1. So we have a 1 solver frequency per flow iteration. Absorption model is a constant absorption and emission. So these are the inputs into the radiation model. So similar to how we have to turn on turbulence, we can actually turn on radiation by giving it this input file called radiation properties. So given that we'll need some of these inside. Alright, so these are the constant absorption and emission coefficients. So since we define a model, we have to give the model inputs, similar to the thermophysical properties. So a scatter and soot model, we both have none. So it's a pretty simple model. But yeah, so it's basically to turn on radiation, we need to put in these files. Okay. And of course, it is useful for us to do a comparison between, say, the SimpleFoam for this hotRoom and the SimpleFoam for, let's say, the one we were doing earlier, which was the cavity. So we can learn how to turn on radiation in any kind of simulation we want to run. Okay, so SimpleFoam, let's see, buoyant cavity. Now clear to bring us back up. And for the sake of time, let me just have a all run n in the background so that we can run the file and then we can see some results. So it's going to do block mesh and buoyant SimpleFoam. Okay, so let's take a look at the 0 files. And let's take a look at the 0 files here. So you can see the only extra file you need to put in for radiation is to have this G on. Alright, you just put this G on and then we have to see, okay, we'll need to specify some boundary condition for G. The theory behind it, I'm not going to go into it, but these are the input files. I'm just going to say these are the input files we need to put in. Okay. So the other thing we can look at is the constant directory, which there will be a polymesh due to our block mesh, but the rest are just same. So let's take a look at the constant. Okay, so we notice there are there's G in both, which is important because there's a buoyancy effect. Next thing we know that it's thermal physical properties, and they are almost exactly the same. Okay, so you can see, except for this, there's a reference pressure, but this is not actually that important for, let's say, the radiation bit anyway. So this is how, yeah, this is slightly different. You can see the molecular weight slightly different, but both actually just refer to air. Constant heat, constant pressure heat capacity, latent heat of fusion, dynamic viscosity, and Prandtl number. They all have slightly different values, but excuse me, same thing. Okay, so we can look at the turbulence properties. One is K epsilon, one is K omega. To us, it's like this doesn't affect radiation at all. So let's take a look at the radiation then. So we'll need to actually have these radiation properties. Okay, this radiation properties file in there, and let's see whether we can find any resource online that talks about how to put these radiation properties. Yep, and this is one of the resources online that talks about, yeah, this is from cfdsupport.com, and they'll tell you, okay, besides just the simple radiation models, in this case it's P1, we can look at other radiation models such as opaque solid. The absorption emission model is always this. In the it's not always absorption, constant absorption emission, but on this page it only talks about constant absorption emission. So we have all these here where we can use different models such as opaque solid. That's one. P1 is the other one. Okay. Yeah, P1 is the other one, which is useful for oh yes, according to this website, yes, P1 works well for combustion applications where there is some optical thickness. Okay, so these are the different kinds, and you might have seen this FVDOM before, finite volume discrete ordinates method. It means that this solves a very much more complicated equation for radiation, and is more accurate, I would suppose, because now the radiation, it should kind of depend on the angle and everything. So yeah, the angle between the two surfaces we are talking about. But of course now we are just doing the simple ones, just letting you know there are lots more what do you call that, models available. So there's no radiation, there's opaque solid, there's a P1, which is this one in our file here. The solar load view factor. View factor is, you should have known this if you study heat transfer in a mechanical engineering context. You know what view factor is about. And this is a discrete tray radiation method, like for apparently lasers. Okay, so let's take a look. Yeah, so these are some of the resources online. I know there are not a lot, but we can go through. The other way is that we can go through these tutorial files step by step, try to understand what's going on. Then hopefully, if there are other tutorial files that have, you know, radiation effects, we can then study them to see what are the effects if we change certain parameters like these these, etc. Yeah. So then we can learn how to access our radiation models from there. Okay, so but this is just some basic radiation model. Okay, and it looks like the file is almost finished. In fact, it is finished now. So this hot radiation room is finished. We can touch red hotRoom.foam. Then we can see what that geometry is like. Okay, let's so the last thing of comparison besides the zero and constant file, we can take a look at the system file to see if there's any differences. Again, the system file here, it creates the input for how to solve the problems in the FV schemes and FV solutions. Block mesh dict, you know what it does. Control dict, you know what it does. So the important thing is to look at FV schemes and solutions and see if there's anything else to add in if you want to add in a radiation effect. So let's see VI FV schemes. Okay, we compare line by line. One it says steady state, Gauss linear. So the first two are pretty clear. Second one, it says divergence schemes. There's no default anything. Divergence of phi and u. There's something. Bounded Gauss upwind. Phi k. You'll see that on both sides. There's a big K. And there's an entry for both sides. H, an entry for both sides. K, an entry for both sides. Phi epsilon, entry for both sides. Phi omega, only in this side because the turbulence model is different. And divergence of rho, new effective, blah blah blah. It's a Gauss linear for both sides. So other than that, there's nothing much else you need to add to do a radiation solver. Of course, you have this wall distribution thing here, which we don't really need to bother about yet if you want to add in radiation, because it's not over in this hotRoom tutorial. Okay, let's take a look at FV solution to see whether there's anything we need to add, any input we need to add in order to enable it to solve radiation. So, okay, let's again go line by line to compare. So P rho GH, we see in both sides. UHK epsilon, UHK epsilon omega, we see in both sides. These are turbulence models. Now, one thing we do note that there is an extra. There is an extra is this G factor. This must be inside the FV solutions. Okay, FV solution file in order for it to be able to compute radiation. Now let's take a look at the simple algorithm. Okay, there's some residual control and non-orthogonal characters. They are there for both sides. And here there's an extra that says momentum predictor no. Okay, so P ref cell 0, P ref cell 0, P ref value 0, P ref value 0. Now again in the residual controls here, you again see that there's a tolerance for G, because this is another field you need to solve for. And again, so 3 places we need to look out for wherever the G pops up. One here, and if you notice the relaxation factors, I'm going to skip the line by line and I'll just tell you straight. The G 0.7 needs to be added here in order for a simple foam to be able to calculate radiation. So now you know what files we need to add or edit for. We need to put in inputs for it to solve radiation. One is this G, the G in the FV solution file, right? And then we also need to add in two parts. One's called boundary radiation properties. One is called radiation properties. These files need to be present. Oops. Quit. What happened? Okay. I pressed the wrong button. Okay. CD back and CD0. We also need a G boundary condition. So mainly the extra bits that have to do with radiation are mainly to do with G, this radiation constant. radiation input file and boundary condition. So if you want to add radiation models, just remember what are the differences in this video. And then let's take a look at the hotRoom results. Okay, buoyant cavities here, hot radiation room. Okay, this one, it means again discrete ordinates method. So this is a more complicated way to get a slightly more accurate model of radiation. So hotRoom.foam, let's apply. So we have this kind of let's take a look, temperature. Okay, you can see this T here. So let's step up time. Better zoom out. Oops. Yeah, so they see that this hot part over here. Let's go all the way up. Okay. Now we see some yeah, okay, I should have rescaled. Now we see some difference. Okay, so initially we have this hot part. This hot part actually heating up. Then as we increase the time, you can see the heat actually spreading. The heat flow actually spreading because we have some convection currents going on. So it's going to the top of the room. So there's a convection and radiation effect, both being displayed over here. So if you want to see a wireframe, you can see like that. So you can see the top and the bottom, what's actually going on. Okay, so there's some radiation, the heat source, the radiation there. So again, this is where it starts. Okay, can you see the bottom? The bottom is actually heated up because of the radiation effect. So that's why radiation is important. Okay, so we keep going. And then the bottom isn't as hot now. Okay, so this is a constant temperature boundary condition. Okay, let's see the temperature boundary condition. VIT. So yeah, it's a temperature boundary condition, and then the fixed walls are 0 gradient. And then the box itself, this is the box that's being heated. All right, this is 500 Kelvin, so it's pretty hot. Okay, so there is a spreading of hot air around the room, and there's a radiation effect as well. So at least in this video, we have seen how buoyantSimpleFoam also can do radiation. We just need to add in a few parameters like the G, and then we added the FV solution, and we give it some radiation properties, the input files. We can kind of copy over and edit, and we saw that, okay, there are many models for radiation. So it's not just the simple ones. We have the discrete ordinates method and all. These are just some of the capabilities. So now we kind of have a rough idea of how to edit the files in order to make buoyantSimpleFoam able to solve for radiation properties. So at least that's all I have for you now in discussing this tutorial. It may not be perfect, but I hope it was informative as we walk through the tutorial. So thanks very much. I'll see you guys next time.